Okay guys, so today we're going to talk about exponents, how you write them, what they mean, and rules that govern exponents. So let's start with probably the two identities, I guess you could call them, of exponents. When something is to the 0th power and when something is to the 1st power. Well, when an exponent is to the 0 power, that means that this right here, this whole expression, is 1. If an exponent is to the 1st power, it's just what the base number is, so here it's 2. Now, basically, the idea we get here is that when a number is raised to the 0th power, it's automatically 1, and when a number is raised to the 1st power, it's just its base number, which is, in this case, it's 2. So, those are two important identities in exponents. And now let's talk about exponents that are to the negative power. So if you had something like 2 to the negative 1 and 2 to the negative 2, let's say, now what would these be equivalent to? Well, right, we just saw that 2 to the 1st power, not to the negative 1 power, was 2, right? So what's the difference here? Well, this negative sign in both situations says that this has to be written as a fraction, because to the negative power means that it has to be in a fractional form. So this is 1/2. If you see why it's like that, well, 2 to the 1st power is 2, but this is to the negative 1st power, so that means that it has to be in the denominator while there is 1 in the numerator. Now, if you take the second situation, what is this equal to? This is the same idea. It has to be a fraction, but what has to be in the denominator? Well, we know that 2 to the 2nd power, 2 to the 2nd power is equal to 2 times 2, right? So this holds true again. If 2 times 2 is 4, and this negative sign means that this is in the denominator, then this has to be 4. So basically the idea of negative exponents is that you write it as if, you know, it was just a regular positive exponent, but you just have to put it in the denominator. So now let's talk about some operation rules of exponents. So let's say that you have two different, numbers. So 2 to the 2nd plus 2 to the 3rd, let's say. Now, there is no way to, add these or anything to do anything. So basically all you have to do in this situation, you can't really simplify it. You just have to cut it up in the two spots and just say that 2 to the 2nd is 4 and 2 to the 3rd is 8. So this is equal to 12. So, and this is another important idea, and I'll tell you. Basically, I'll show it by an algebraic definition. This is your idea of the exponent. You have some base that's you just have a base number, and then you have an exponent number right here. So the A number basically tells you what your base is. So let's say this is 2 to the 3rd in this situation. Well, your A says you have 2. And what your exponent tells you is how many times are you going to multiply it by. Well, it says 3 here, so we already have 1, 2, 3. And this is equal to 8. So basically the exponent determines how many times you're going to multiply the number by itself. So, yeah. So now I'll talk about, exponent rules. So let's say that you have 2 to the third times 2 to the second, let's say. Now what is this equal to? Well, this is equal to 2 to the 3 plus 2. Now, why does this work, you might ask? And I'm going to prove this to you. We know that 2 to the third is 8, and we know that 2 to the second is 4. So this is 32 right here. So, and we just said this has to be equal to 2 to the fifth. And what's 2 to the fifth equal? That's equal to 32. Now, the only situation this works is if the bases are equivalent. Okay? You can only do this with multiplication if the bases are equivalent. So that the only reason that you can add these exponents together to get over here is that they have the same base. Now, if these had different bases, you could not do it because it would not maintain equivalency. So, yeah, with that, if you're multiplying exponents, they have to have the same base in order to add their exponents if you want to simplify it. Now, if you have the situation where you have exponents, let's say, being divided by each other, let's say 2 to the fourth divided by 2 to the second. Well, what is this equal to? And this is how I'll explain it. This is equal to 2 times 2 times 2 times 2. And this is equal to 2 times 2, right? So what can we do here? We can cancel out some numbers. So these 2's will cancel and these 2's will cancel. So you can rewrite this to be 2 to the second. You can rewrite that to be 2 to the second. So, and is this expression true? Is 2 to the fourth over 2 divided by 2 squared equal to 4? Well, let's look here. Well, 2 to the fourth is 16, and 2 to the second is 4. Does that equal 4? Well, yes, it does. So we just proved this identity. And again, the same idea happens here as it did with multiplication. To simplify this, they have to have the same base number right here. If they do not have the same base number, you cannot simplify them like this. So, yeah, now I guess the next way of doing it is to say, well, let's say they had the same exponents. Let's say, you know, let's say it was like 5 to the second. Well, that's kind of a big number, so well, when we do it out, 5 to the second plus, it's 3 to the second plus 3 to the second. What does that equal? Well, again, if they have the same exponent, as you see they have here, they both have 2, and they have, well, in theory, they don't actually have to have the same, they do not have to have the same base number because of this identity. All they have to have is they have to have the same exponent. And this is a unique situation, but I'll show you in a different situation to prove it to you. So what is this equal to? We know that 3 squared is 9 and 3 squared is 9. So what is this equal to? This is equal to 81. But what is 81 equal to? That's equal to 9 squared. But look what we had here. We have the same exponents here, and we have 2 numbers of 3. So how did we get that? All we just did was we said 3 times, well, 3, that's equivalent to 3 times 3 to the second. That's all we did there. So when they have the same exponents, you can just multiply their bases together and you'll have a equivalence if you wanted to simplify it. Now let me show you a different situation. the situation that they have different bases, because I don't want you to think that you can only do this if their bases are the same. They just have to have the same exponents. So let's say you had 4 to the second, 4 to the second, 4 to the second times 4 to the second times, oh crap, yeah, I just thought about that. I wrote that last one wrong. Let me go back and do that again. I was totally not thinking through that. I wrote 3 to the second plus 3 to the second equals 9 to the second, which is equal to 81. This is not true. This is 9 plus 9, which is equal to 18, which is not equal to 81. What did I do wrong here? Well, I made the new mistake, obviously, and basically this only happens when you multiply. So what this would have to be, have to be 3 to the second times 3 to the second. Now, if two exponents are being multiplied by each other and they have the same exponent, then you can just multiply the bases together and you'll have equivalency. So we know that this is equal to 81, which this is equal to 9 to the second, which this is equal to 3 times 3 to the second power. So yeah, sorry about that. I totally had like a brain fart there. So yeah, when you have two exponent numbers being multiplied by each other, if they have the same exponents, but they have if they have the same exponents, all you have to do is you can rewrite it with that same exponent and just multiply the bases. In this case, it's 3. Now let me show you a situation if I don't, butcher this like I just butchered that for you. I'll show you the situation of, let's say they have different bases. So if you had 4 to the second times 2 to the second, well, what does this have to be equal to? Well, we have the same exponents, so we know that we can just multiply the bases together. So this is going to have to be equal to 8 squared. So what does this mean? Well, we just took, we saw that they were both to the second power. So basically we just did this. We just said 4 times 2, which is 8, squared. So with that, let me now show you that this is equivalent. Basically, 4 squared is 16, 2 squared is 4, and is that equal to 8 squared? Well, 64 is equal to 64, so we just proved that identity. Now let's prove the idea if they are let's say you have a base of an exponent raised to another base of an exponent. Let's say you had something like 2 to the first, and let's say we raise this to the second power. Well, what would you do in this situation? Well, all you do is you would basically, this is equivalent to 2 to the 1 times 2. Now, how do we know that this is true? Well, 2 to the first is 2, and then we know 2 to the 2. We know that 2 to, you just multiply these, 1 times 2, so this would be 2, and we know 2 to the 2 is equal to 4. Now let's prove this. We know that 2 to the 1 is equal to 2, so we just rewrite that, and we still have this 2 out here, so we know that that's equal to 4, so we just proved our identity. Now again, it's important for this idea that you have a base, of course, and that these two numbers that you multiply them together. That's an idea of exponents. So now let's go into 1 second. Let's go into one other thing. Let's go to exponents that have, fractional meaning, and if they were negative fractions or positive fractions. So let's say you have something like 4 to the 1/2 power. Well, what does this represent? This basically represents that, this is equivalent to the square root of 4. And it's just implied that that is there. If you just write the square root symbol without a subscript here of your number, it's just assumed that that's 2. So, in this situation, 4 to the 1/2 power is equal to the square root of 4, which is equal to 2. So, all the exponent, when it's to a fractional thing, just means the square root of that. Now, if I had the situation, let's say, I don't know, 16, or let me think here. Let's say, you had something like 125 to the 1/5 power, okay? This is equal to the square root of 125. Well, actually, you want to call it the square root, you'd call it the 5th root of 125. So basically here, I won't simplify this, but basically you'd find what the 5th root of this was. So, what number multiplied, 5 times will give you 125. So now let me show you the concept of if it was to the negative power. And it's a very similar idea of what we introduced earlier with negative whole exponents. So basically what this says is if we have like 4 to the negative 1/2 power, well, what is this equal to? Well, we know that 4 to the 1/2 power was equal to the square root of 4, which is 2. Well, again, that negative exponent means that now we're in the denominator, so this is 1 over the square root of 4, which is equal to 1/2. So when it's a negative exponent, that means that it's that root in the denominator, and the root that you're trying to find will be this number. In this case, it's a square root. So yeah, and these are with radical exponent properties, but yeah, so that's basically the general outline of exponents and the rules that govern them. And the reason why it's important to know that these characteristics of exponents is that typically you want to simplify exponents as much as you can, and with these methods of their exponent rules with multiplying, dividing, and these sort of things, you can simplify expressions so that they're easier to work with. So yeah, that will be the end of the exponents video. Thanks for watching, and like and comment on this video.